We have seen that the work done by a force through a distance depends on the force and the distance, whereas it is independent of the time interval over which the force is exerted on the body. However, it is oftentimes not only important to determine the work done by a force, but also how long it takes to do that work. In order to describe the rate of the work done by a given force with respect to time, we will introduce a new quantity called power and denoted by the letter P. We define the average power P of a given force as the ratio of the work W done by the force to the time T required to complete the work. In other words, power is equal to the work done in unit time. Since the unit of work is given by the product of the unit of mass, the unit of length to 2, and the unit of time to -2, the unit of power is equal to the unit of mass times the unit of length to 2 times the unit of time to -3. In SI units, power is given in kilogram meter squared per second cubed, which is called watt with the abbreviation W, and it was named after James Watt. Then we can write that 1 watt is equal to 1 joule per second. Based on the definition of the average power, we can introduce the power P of a given force acting on a body as the derivative of the work W done by the force with respect to the time T. The definition of the average power also helps us to express the power P of the force F performing the work delta W on a body over a small time interval delta T, if we substitute the scalar product of the force F and the displacement delta S covered by the body over the time interval delta T into the work delta W. Then the instantaneous power P of the force F over the time interval delta T is given by the scalar product of the force F and the ratio of the displacement vector delta S to the time delta T. By taking the limit of this expression as delta T tends to 0, we can write the ratio as the derivative of the displacement delta S with respect to the time T, which is equal to the instantaneous velocity v of the body. As a result, the instantaneous power P of the force F is equal to the scalar product of the force F acting on the body and the velocity v of the body. This formula also holds for the work W done by the force F along a given curve C between 2 points A and B, which is given by the line integral of the force F with respect to the arc length S over the curve C between the points A and B. The line integral can be expressed as an integral with respect to the time t over a time interval with the boundaries ta and tb representing the time measured when the body is at the points A and B. Here the derivative of the arc length with respect to the time t is the Jacobian of the transformation applied to the integral, which is the instantaneous velocity of the body moving along the curve C. Then the work W done on a body by the force F along the curve C between the points A and B is equal to the integral of the scalar product of the force F and the velocity v of the body with respect to the time t over the time interval between Ta and Tb. This expression can be inserted into the definition of the power P, which is equal to the derivative of the integral with respect to the time t. By applying the fundamental theorem of calculus, we can write the right-hand side of the equation as the scalar product of the force F and the velocity v. As a result, the formula stating that the instantaneous power P of the force F exerted on a body is equal to the scalar product of the force F and the instantaneous velocity v of the body also holds in the general case. If the second law of motion is substituted into this expression obtained for power, then the power P of a force F acting on the body of mass m can be expressed as the mass m times the scalar product of the body's acceleration a and its velocity v. This result also shows that the power of the force exerted on a body vanishes if the instantaneous velocity and acceleration of the body are perpendicular to each other. We have already seen that the work always vanishes in the case of constrained motion, and this formula obtained for the power, that is the rate of change of work, is also a consequence of this fact. For example, if a ball is attached to a string and whirled in a circle by hand, it will perform uniform circular motion, where the centripetal force F points towards the center of the circular path of the body, and so does its centripetal acceleration a. Here the acceleration of the body is always perpendicular to its instantaneous velocity v, which is tangent to the circle. Therefore both the work done by the centripetal force and its power vanish during the motion.